Awesome. So I'm going to talk about how Twitter is trying to start using something new, persistent memory, in our environment. I think the high-level message I want to send here is we are not as capable as, for example, Oracle to build an exciting new product using multiple new technologies, spending years of effort in giving you sort of huge gains. That's sort of not what we're trying to do here. As someone who runs a service or applications, one of those people who does things that is above you that probably doesn't make any sense most of the time, what I want to sort of have people take away from this is what is the shortest distance from what you have now with traditional hardware and a data center that someone else designed, right? A hardware team or maybe you're in the cloud, to a place where you can have a taste of new hardware without breaking all the norms of operations that you understand and without spending a lot of resources in advanced commitment, which we don't have, and still get a sense of whether this is worth it, how does it work out, would it be reliable enough in production, is it worth a follow-up investment? So it's a compared to basically access data, consider this a piece of cake, right? It's a very small problem. So I want to talk to you about Pelikan. Pelikan is something that you probably have never heard of, but fear not, it's actually very, very easy to understand. I imagine everybody has at least heard of Memcached and Redis. So Pelikan basically can act as either Memcache or Redis or both. So what it is a open source modular cache. So the architecture, if I have to give you a high-level view, will sound very, very similar to Redis and Memcache. It's a key-value store that stores data in memory. We use it strictly as a cache, not as a database, so we never thought about consistency, and I prefer to keep it that way if possible. A little bit of background of how we run cache at Twitter. I think this is important because this explains the test setup that we later will present. Right, so we have, I think, an interesting, maybe a little bit unique setup where we are, in terms of cache, we're in favor of single tenant configurations to achieve good resource isolation. What that means is we have a very large number of relatively small clusters, ranging from a few thousand QPS maybe all the way to maybe tens of millions of QPS per second. And we run tens of thousands of instances over a hardware cluster that has maybe many thousands of nodes. So because of this configuration, you can see that we have to have multiple jobs running on every single node. So we tend to run small and wimpy clusters. So each job actually only takes up a few cores and uses a few gigs of memory in most cases, and sometimes spikes up to a larger size, which I will explain later. So our SLO is, decent, but nothing crazy. We're a web company. Nobody is in a hurry to get anywhere. People are there to kill time. So, and also, and also, if you know anything about end-to-end performance, most of the people spend the time finding the cell tower that's nearest to the cell phone, right? So the latency happening in the data center actually is not a dominant part. So our SLO is at a decent 5 millisecond at the tail part, P999. As long as we have that, we're actually quite happy. So the project Pelikan actually aims to support all the well-known and maybe not well-loved protocols out there, Memcached, Redis, Thrift, don't deal with that, and data structures that may or may not be relevant to you. So what is interesting about Pelikan, I think, for this audience in particular, is that I think it makes a lot of the experimentation less painful if you are not a software developer who already knows some of the open source projects like the back of your hand. Right? So handling key value requests is actually a very standard process where you would read some data from the socket, parse it, and then process it and write a response and send it off. Right? So in doing so, we also need to deal with some data structure that is putting some kind of data storage. So if we do this abstraction correctly, then you will have something that looks more or less like what is on the left side, where you would delegate the parsing and composing to one module, you would delegate the RPC stack to an entirely different sort of invisible component if you can do that. And also you will layer the data structure on top of a well-defined data store module. Right, so this is what gives the project the capability to mimic multiple services like Memcached or Redis without having to basically duplicate all the code. So we'll see why this modularization is helpful in adopting PMAM. So okay, going into PMAM, well, Intel insists I have to have the full name, so there you go, a very unbalanced slide. Just very quickly, everybody here already has heard of this like 10 times, I believe. If you want to use persistent memory, there is the memory mode and there is the app direct mode. Right? So the memory mode has the benefit of giving you suddenly more memory without any code change. It is, of course, volatile. You don't get to persist, but if I'm operating cache, I actually don't care. And you can also use the app direct mode where the PMAM is no longer, the DRAM is no longer hidden from you as cache. You suddenly have direct access to both, and you can make wise decisions if you have them, and also persistent. So for us to try PMAM, we actually have a couple of considerations going into this. First is, more memory is always better. We have 400 or whatever number of clusters, and some of them are memory bound. Actually, a lot of them are memory bound. So for the clusters that are memory bound, having bigger, cheaper memory is a very sort of straightforward TCO play, right? You reduce the cost if you remove that or shift that bottleneck. The other thing, and by memory bound I mean limited by the size of the memory, right? We want to put more data into memory to serve them out of cache, and that's the limiting factor. And also the flip side of that is now if you have more memory that you can use, more requests actually will end up as hits at the caching tier. And what that means is you will reduce the amount of traffic that goes into sort of the deeper level of the stack, which tends to be more expensive and slower and have some other sort of undesirable features. So that affects both scalability and cost. So generally having a very, very warm cache is favorable, especially for workloads that we have at Twitter. Many of our data sets actually can be cached up to like 99.9%. So you almost never see the database. And the other side of things are sort of actually trying to consider the persistent aspect of the memory, because one of the operational problem we have is anything that's in memory, when you restart it, it goes away. So if we are so reliant on cache to being warm, then whenever we lose a warm cache, it becomes a problem, a capacity problem for the back end, and also becomes a sort of a performance or availability problem for the high-level request, which tends to fan out to many, many backends. So having a warmer cache means if we can reduce the sort of the data loss when we do routine operations, which are binary upgrade or host maintenance, things that tend to complete relatively fast, but inevitably forces us to give up data that's already in memory, that actually would be an operational win. The other thing is having higher availability during maintenance, like for maintenance not to be such a event that makes the entire site more vulnerable because the cache rate goes down, it's good for the site reliability overall. So we also have a couple of constraints, right? I said we don't really have all the resources we can sort of at will to drop into an experiment like this. So what is important is for the changes we make to be small and manageable. We can sort of dial up and down the investment as we see fit. So that means we want the change to happen in the same code base that we already have. It should be not very invasive. It doesn't require you to rewrite everything. And also, it doesn't change how developers interact with it from the way they already know. And then finally, last but not least, operability is extremely important if you're a service owner. So being able to sort of enable PMM at the time of launch, you don't have to build any special binaries for it. You don't have to do complicated procedures to deploy it. This is all very important. And also having predictable performance is the one thing that will keep people from being woken up by pages in the middle of the night. And I was on call for 7 years. I care about this a great deal. So here is why the abstraction matters, right? So we saw that the cache can be abstract as a bunch of boxes, and actually the data store is only a very small part of the abstraction. And it proves to be, so it turns out that if we do the abstraction right with memory, this little component is all we need to care about to enable PMM. And in particular, what we did, actually what Intel did, I actually did not write any of the code that is on this slide. So thank you, Intel, for doing my work. What Intel did is they created a data pool abstraction on top of existing CLib, libc APIs, as well as PMDK APIs. So there are two paths, right? First, we can have a compatible mode. If you don't have PMM, you just fall back to DRAM. And on the other hand, you can have persistent memory where we take advantage of the PMDK library, and also we can use file-based, file-backed memory that is still byte addressable. So essentially, data pool will present the same API to the upper level abstraction, such as, you don't need to understand what slab and cuckoo mean too much. If you forget about it, that's fine. But the concept is the interface is very small. So we have essentially two ways of using memory, right? So slab is what you probably are familiar with. You have a bunch of memory that get chunked into different sizes to use as key value store containers. And cuckoo is another one that looks like a giant array that gives you a little bit better memory efficiency. In both cases, the modification we need to do to enable PMM is actually quite limited. Let's see. So if you only have DRAM, of course, everything goes into DRAM. When we make the change to use PMM, for the cuckoo use case, because everything is in one giant array, we just shift that whole thing to PMM. And in the slab case, we keep the hash table in DRAM, and the vast majority of data goes to PMM. So this is basically the philosophy is let's try to put as much data onto PMM as possible, because that's where the space is, and see if the performance is good enough. So let me talk a little bit about the result. I think this is the one thing that's interesting about this project is the code change actually was very, very simple, mostly because we have it done by professionals, and partly because the abstraction works out well. So to enable data pool was about 300 lines of C code, so anybody can do that in a reasonable amount of time. But on the other hand, because we aim for this final product to go into production at some point, I don't know when that exactly will be, but that's the goal. So it's really important that we test it out thoroughly. So this is how we test it to gain confidence. So first, we try to mimic core parameters that replicate what we see in Twitter's production, right? So we pack every host with many instances. We have object size distribution in a way that reflects what is the most typical, that covers most use cases at Twitter. We also have dataset sizes that is comparable to our production configuration. And one notable thing is we have a much larger number of connections per server compared to most of the Memcache Redis benchmark you will see, because this is what we have. And it turns out actually the network performance is quite important. And we also have a couple of different rewrite ratios just to see if the workload is sensitive to that. And the focus is we sort of define 3 stages of evaluation, right? So every stage, at the end of every stage, we try to see, should we go or should we not go? So the first stage is just use the memory mode and see if this makes sense at all, right? It's like a vanity, it's like a sanity check. And then we enable app direct mode and see for the operational gains that depends on app direct mode being enabled, do we get the benefit that we were expecting, and do we have any performance surprises when we switch from memory mode to AppDirect mode? And finally, we want to run, so until now, all these experiments have been run on Intel's, in Intel's lab environment, because that's where the hardware is. And the last stage is when we finally have equipment in our data center. We want to redo the tests, use slightly different hardware, but is exactly what we will get if we are running in production. Basically, lots of thorough testing to make sure all the numbers are solid. So stage 1 is actually very, very boring. So the only interesting part you can see, that's the dip, is when the packet size, when the object size exceeds 1 MTU, so you have a throughput drop. That's exactly what we'd expect. And in terms of latency, it's actually more or less flat. So the line chart is about latency, and the bar charts are about throughput. So we change the object size. We change the amount of data that resides in DRAM versus in PMEM by just keep dialing up the size of the total data set. So as you go to the lighter shade, actually more data will be residing in PMEM, and there is very little difference in throughput and latency. And note this is a sort of a loaded configuration by Intel with the best CPU and a 222 configuration, so lots of bandwidth to go around. And then we move to stage 2, right? So stage 2, we have AppDirect mode. And again, kind of boring. It's slightly more interesting than the previous chart because the latency numbers start to move a little bit. But the throughput numbers are actually still pretty stable if you look at it. But overall, what we found out is, and also in this chart, we dropped the largest payload, which is 2K. So we keep it all under 1 MTU. To keep the experiment a little more manageable, right? So we see what we would expect, that latency goes up as the value size goes up, but not by that much. Also, if you look at absolute number, 200 microseconds is well within our defined SLA. So the other aspect of the AppDirect mode exercise, right, is do we get any benefit from having persistence in our memory? And so again, to sort of go back to why we were incentivized to do this, having data available quickly after maintenance is actually something that's valuable to us. So really, the shorter the window it is to reload the data from persistent media into a serving state, then the more valuable this is to our maintenance. And it turns out that rebuilding our data from rebuilding the slab hash table from data that's otherwise stored on persistent memory takes only a pretty reasonable amount of time, right? So to rebuild 100 gigabytes of data, it takes 4 minutes. If you do 18 instances concurrently and load all the data, it takes 5 minutes. So compared to what we otherwise have to do, which is we need to wait 20 minutes between starts, this is a sort of order of magnitude improvement on how long we need to wait. Because the 20 minute only applies to a data set that's much smaller. Keep that in mind. So we believe there's a lot of other changes that needs to happen before we can turn on the beast of loading from persistent media into production. But I think the raw numbers are supportive of us having some benefit for cache by putting data on persistent memory. So finally, the last stage, we bring everything in-house, and just don't. The one principle about benchmarking is don't trust anybody else's benchmark. So you should never quote my benchmark numbers in your internal report, say in supportive or rejection of a decision. Always do your own benchmark, because in this case, the numbers are somewhat different. I think the primary, we have not confirmed 100%, but the primary reason we think this is the case is because different from the Intel lab, what we have is large quantities of middle-of-the-road Intel chips, and also a much less loaded configuration. We have the 211, so that means we are losing 2/3 of the channels compared to the lab configuration going to PMAN. Right, so in this case, then we're going to see more bandwidth contention if we use things in a way that stresses that. And this is shown in this test, right? So you can see that compared to, you can see that the P999 latency, where the SLA is drawn in the middle, we start to drift above this SLA in memory mode when most of the data is in PMAN. Again, I think this is because we don't have as much bandwidth. However, when we switch to testing AppDirect mode, everything falls back to normal, right, by expectation. So this is acceptable again. I think this is interesting because I was not expecting too much of the performance benefit between going to AppDirect mode. But what this tells me is actually with AppDirect mode, it's easier to control tail latency compared to memory mode just because data placement is explicit. So that's a good lesson to learn. All right, so overall I think this exercise shows that memory mode is a very good gateway drug if you want to get hooked. So remember, one thing about application developer and software engineers in general is we do not know what's going on with hardware at all. We don't pay attention. And we have no idea how to predict how much effort it takes to do anything that relates to new hardware. So I feel the most important in continuing this discussion that has, it's sort of like a mini panel in the form of 4 presentations in a row is I don't think PMAN without consistency is worthless. I think one of the adoption bottleneck is really software engineers are not paying attention and they have no time. So whatever can lower the barrier to get something out of their existing software, get them to think what is possible if they spend a little bit more time in terms of architecture redesign and just use their imagination. And once they learn the property of the hardware, actually, I think over time, all that insight will sort of permeate above all these layers of stack, and sort of invite people to create something that's new and exciting, right? But the thing is, you need to get people started somewhere, and I think memory mode is a great place to start. And over that, if we can use the correct abstraction to gently guide them to persistent memory and make it easy to swap one thing for another, add more complexity of how to deal with all the new properties, and then I think we will see more benefit on top of what people think they were getting going into the space. So a little bit of tidbit is after we got equipment from Intel and running the benchmarks in our production, in our data center, I actually started canarying persistent memory in production. We only do it on one instance out of the hundreds of instances that's serving people's tweets. So if you tweet enough times, one of those tweets will be served out of persistent memory. Well, I'm strictly forbidden to tell you which one it is. I don't know at all, but I know probabilistically, if you tweet enough, one of them is going to be served. And it's been running in canary mode since the beginning of since before the holidays. See, this is the nice thing about it. I don't have to think about how long it's been running fine. So that's it.
That's the best endorsement of information technology that I've heard. I don't have to worry about it because it's running. So thank you very much. Thank you.
Thank you.
Here we go.